Recording didn't work out so well, so hopefully this will. So on the left-hand side, I'm going to teach you a couple of symbols that you should know for this lesson before we begin. Anybody know what this funny-looking Z stands for? No. I did tell you at one point, yep. Yeah, what was that? Those are the integers.
Like real numbers?
No. Integers, right? That's a subset of the real numbers. The real numbers is like everything. Integers are just like the 1, the 2, the 3. And I'm going to put a little plus sign, mean positive integers, okay? So what does, if I make a upside down capital A, this is the symbol that stands for all. Okay, this is shorthand writing for all. You guys are getting into the secret world of mathematical handwriting here. And then if you have 3 little dots in a triangular formation, that means therefore. Okay, we're going to use all these symbols today. Okay, so what we're going to do is I'm going to tell you the principle of mathematical induction. We're going to go over it step by step. And the book teaches it a little bit differently than I do, okay? The book breaks it down into 2 conditions, condition 1 and condition 2. And I break it down into 3 steps. I think 3 steps is a little bit more approachable for the applications that we're going to do. So if you're starting off with the principle, if you're given some statement about the positive integers, or n. So just like, as an example, like this statement, I've been given a statement about the integers, okay? It's an if-then statement. If 3 things happen, then you can say that this is true for all integers. So let's set up the 3 things, okay? The first step is pretty easy. The first step is to show that the statement is true for n equals 1. So the very first term, you have to show that it's at least true for the very first term. That's the first step. The second step is then you show, or excuse me, not show, you assume that your sequence or your statement is true for some n equal to k somewhere down the sequence. And I'll explain more about that later. It's okay to have a confused face right now. And the third step is, so first we're showing, then we're assuming, and then the third step is we're proving, this is where the proving part comes in, proving that the statement is true for the next term, k plus 1. If you can do all 3 of these things, then your statement is true for all positive integers n. So we get this cool handwriting at the bottom there to sort of process is called mathematical induction. So this whole entire process here is the process of mathematical induction. So it's a process. And all right, yeah, you can try it again. Okay. What we're going to do is we're going to actually prove that first statement that we had at the very beginning. And it was, so we're going to use the principle of mathematical induction to prove that this is true for all positive integers n. We had 1 plus 3 plus 5 plus blah, 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 plus, what was it? Was it 2n minus 1? Is that right? Equals n squared. All right, let's use mathematical induction to prove that this statement is true for all positive values for n, positive integers. So step 1 of the principle mathematical induction says that we have to show that this statement is true for n is equal to 1. So here's what they want you to do. You have to show that 2 times 1 minus 1 is the same thing as 1 squared. So notice I'm taking the left-hand side, setting it equal to the right-hand side, and substituting a 1 to show that this is true. If it wasn't true, then I can stop right away, but these are going to also all work out. So 2 minus 1 equals 1. Yep, 1 is equal to 1. Check. So I've done the first step. The first step is easy. You guys down the first step? So far, so good? Okay, let's go on to step number 2. Step number 2 is you assume that your statement is true all the way up until some n equals k value. So what do I mean by that? Okay, here's what I mean. I'm going to assume that 1 plus 3 plus 5 plus blah, 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 plus all the way up to 2k minus 1 is equal to k squared. So k is somewhere in your sequence, right? It's before you get to n. It's just somewhere along in that sequence. We're going to assume that up to the kth term that my sequence is holding true. So what did I actually do here in step 2? I didn't do anything fancy at all. Who can explain what I did? There you go. I just substitute a k for n. That's it. That's all I did. That's basically step 2. That's the piece I'm assuming is true. I need you to write it out every time. Okay, then the third step is I need to prove that my statement is true for which term? Not the nth term. Let's go back up here. It says the k plus 1th term. Okay? So, in terms of sequences, where is the k plus 1th term? It's right after the kth term, right? If I go all the way up to the kth term, then what's the very next term? K plus 1. That's easy, right? So here's what we do. We write out 1 plus 3 plus 5 plus yada 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 plus all the way up to 2k minus 1. I copy identically what I have up there in step number 2. And then I pause and I take a break. And a breath. Then I need to go up to n equals k plus 1. How far have I gone so far in my sequence? Only up to where? K. I need to add on the next term. So how do I generate the next term? What do? I replace k with k plus 1. So I replace this with 2 k plus 1 and then minus 1. So here's what I did, right? I took, wherever I saw my k, I added a k plus 1. You guys with me? Okay, now, if I change the left-hand side, then I also have to change the right-hand side. So if I add all these up to k, it's equal to k squared. So if I go all the way to k plus 1, then what does the right-hand side have to be? K plus 1 squared. There we go. So step 3, this is the setup and solve part. We haven't proved anything yet. We're not there yet. This is just setting it up. No, the story has a much better ending. Okay, so our goal is to make the left-hand side of our equation look identical to the right-hand side of our equation. So looking at it from here, it doesn't look anything like it at all, right? Here's the trick. You have to remember, I'm going to put a big box around this stuff right here. And this is what I want you guys to do every single time you do it. And I want you to ask yourselves, what is the stuff in the box equal to? Yes, all the stuff in the box is equal to k squared, isn't it? So that means I can replace that with this, k squared. Plus, now let's distribute over here. What's 2 times k? 2k. What's 2 times 1? And then minus 1. Equals, on the other side, k plus 1 squared. If I can get these two to look like each other, then I have proved its truth for all n using induction. Okay, here we go. Does anyone see any like terms I can simplify? K squared plus 2k plus 1 equals k plus 1 squared. Hey, can we factor that? I told you. You guys don't believe me. So isn't this just k plus 1 times k plus 1? So, oh my gosh. K plus 1 squared equals k plus 1 squared. Now, you tie it all together by doing this. Therefore, statement is true for all positive integers n. So, let's prove that this is true. Let's prove 3 plus 6 plus 9 plus blah, 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 plus 3n is the same thing as 3 halves n times n plus 1. All right. Yes. Well, we're going to prove that it works using the principle of mathematical induction. Okay, what do we do first? What's the first thing we do? I like it because there's steps to follow, right? Okay, what's the first thing we do?
I'll show that it's true for the first term.
Nah. So this is true for n equals 1. So we're going to say 3 times 1 is definitely the same thing as 3 halves times 1 times 1 plus 1. Yep. 3 is equal to 3 halves of 2. Yep. 3 equals 3 because the 2's cancel out. Check. Step 1, done. Step 2, what's step 2?
You assume that it's true for n equals k.
Assume it's true for n equals k. So what does that actually physically look like? It looks like this. 3 plus 6 plus 9 plus blah, 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 plus 3k has to sum up to 3 halves k times k plus 1. We agreed? Step 2, done. Easy enough? Step 1 and 2, that's no problem. Step 3, the setup and the solve, that's where everybody gets hung up. All right? Okay, step 3. We were trying to prove true for what? For the next term. For n is equal to k plus 1, which represents the next term. Okay, so what does that physically look like? It looks like this. 3 plus 6 plus 9 plus blah, 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 plus 3k. Then I stop. I go, okay.
Can we box that right now?
Hold on a second. I guess so if you want to, yeah. And we're going to put a box around that. But we've only gone up to the kth term. We have to add on what? The next term. So that's going to be 3 times k plus 1. Now, on the other side, we have to replace every k with a k plus 1 because we're going to the next term. So I'm going to have this 3 halves. Now watch what I'm going to do for you for highlighter's sake, okay? This k over here becomes my new k plus 1. So notice I replaced that k with a k plus 1 term. You guys cool with that part? Now,
K plus 1, check it out.
There's 2 k plus 1s. That's weird.
no, I have a k plus 1. Yes. If this, you know what this becomes? It becomes this. Yes. K plus 1 plus 1, which becomes k plus 2.
What just happened? How did that become k plus 2?
Because you substitute k plus 1 for k, dog.
K plus 1 plus 1.
I get it.
All right. So that's the setup. And now we ask ourselves, what does the stuff in the box equal? The stuff in the box is equal to that right there. It's always equal to the right-hand side of step number 2.
Well, that's what we're trying to prove.
Oh, yeah. We don't know that. Yeah, exactly. Okay, so here we go. I've got 3 halves k times k plus 1 plus 3 times k plus 1 has to equal this stuff. Now, if you can make the left look like the right, that's it. You're done.
Wait, what's that?
Okay, so our goal then, right? Our goal is to make the left-hand side look like the right-hand side. Does anybody notice anything about, this is the trick here. Notice I have a k plus 1 there and I have a k plus 1 there. Do you see that? I can factor out a k plus 1. I can factor by grouping.
And you have a k plus 3, which is totally equal to k plus 1.
And then what do I have left over? I have 3 halves k plus 3. Whoops, I don't want to use red here. I have 3 halves k plus 3, supposedly is equal to this stuff. I'm close, aren't I? I have the k plus 1 there. No problem. I have this piece there. All I need is the k plus 2 piece over here, don't I? Okay, how do I get it? Here's the trick. Once you see the trick once, you use it over and over again. So k plus 1, just factor out a 3 halves. And then ask yourselves, 3 halves times what is 3 halves k?
K plus 2.
K. And then 3 halves times what is equal to 3? 2. Ha! Well, there it is. Bang. You're done. You got it. Slick, huh? Super slick. Therefore, finish it up. Therefore, your statement is true For all positive integers n. Woohoo! And you look like Matt Damon in the whole, You guys have never seen that movie, Will Good Will Hunting? Where he's writing on the mirrors? They're writing all this kind of stuff down. You guys ever seen that movie? Am I the only one in the room that's seen that movie? Good Will Hunting? You guys have never seen that movie? Oh my gosh. Your homework for... Okay, here we go. 1 plus 2 plus 3. You guys remember this one? The whole story about little Gauss who added up all those numbers? N times n plus 1 over 2. Let's prove that his thing was true, that he came up with in his head. So the sum of the first, 42 numbers is just 42 times 43 over 2. Crazy. How does that work? Let's see. All right, step 1. What's step 1, you guys? Show true for what? For n equals 1. So let's see here. Does 1 equal 1 times 1 plus 1 over 2? Yep. 1 equals 2 over 2. Check. Number 2. Write it out. 1. Or you assume. Bless you. True for n equals k. So what does it look like? It looks like 1 plus 2 plus 3 plus yada 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 plus 3k is equal to oh, sorry. Dude, come on, calculator. I meant to say n. N is equal to, oh my gosh, it is late in the day. Sorry, k. K times k plus 1 over 2. Sorry about that, team. Now, step 3, here we go. Show or prove true for n equals k plus 1. All right, let's write it out. Let's physically look at it. It looks like this. 1 plus 2 plus 3 plus yada 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 plus k. All right, take a break. Box it. Point to this stuff. And then add on the next term. What's the next term? K plus 1. So that looks like k plus 1. That's a pretty easy one on the left-hand side, right? On the right-hand side, though, we need to replace every k with a k plus 1. So that's going to look like this. K plus 1 times k plus 2, yes, divided by 2. All right. Now, make the left look like the right. And you've earned the right to use the fancy notation. So what is all the stuff in the box?
K times k plus 1 over 2.
Plus k plus 1 equals this stuff. All right. It's close, huh? I got that k plus 1 there. What's going on the left-hand side? What am I doing on the left-hand side? I'm adding what? I'm adding fractions, aren't I? And what do I need to do to add fractions? Which would be 2 over 2, right? Have I done anything illegal? No, I'm just multiplying a fancy 1. And I'm allowed to multiply by a fancy 1. Okay, so... Oh my gosh, did you guys see it already? Check this out, right? I've got... why are you so slow right now? Okay, I got that and that. So I can factor out a k plus 1. What am I left with? Oh my gosh. So rad. Big happy face. Yeah. Therefore, this thing is true for all positive integers n. And I'm going to stop my recording because I think I've gone too long, okay?